This work is a collaboration between University of New Mexico and University of Alabama, Huntsville on the study of a jet and crossflow. The setup is probably familiar to most of you because of its considerable practical importance. Let me also note that this problem is interesting to a modeler because you have relatively simple and well-defined conditions from which a very complicated flow behavior emerges, at the very least when you are injecting gas into another gas at a subsonic speed. You will have that jet bending into the flow and developing into a counter-rotating vortex pair. There will be these leg-like wake vortices which will connect the jet to the wall. There will be a horseshoe vortex which will form upstream of the injection point. If the main flow is supersonic, you will also have a separation shock, a bow shock, and a Mach disk in the jet. There will be mixing, there will be turbulence, and this is just for the gaseous situation. Sometimes it's more advantageous to inject fluid into the flow, like if you want to develop a more efficient jet engine. And that fluid can be transcritical, subcritical, or supercritical. Most useful practically are transcritical and supercritical injection setups. These bring their own challenges, however. So if you inject fluid into a gas flow, it breaks up into droplets. Droplets manifest themselves on multiple scales, and that makes modeling something like this quite computationally expensive. For supercritical and transcritical jets, phase transition of the injected material also becomes very important and happens on the relevant time scale, so you have to model that. Plus, you also get some intermittency. Although the penetration length of your jet may become shorter, there will be pockets of fluid popping from the core of that jet and propagating further into the flow. Commercial codes cannot really handle this. They are not validated for this problem, and sometimes they will also lack the computational oomph. Diagnostics in experiment, interestingly enough, are also limited because you cannot just do straight up PIV or laser-induced fluorescence, because some part of your field of view and your laser sheets will be blocked by the fluid present in the flow. Our approach to this problem is to gradually increase the problem complexity using the same experimental arrangement. Start with injecting gas, then graduate to injecting fluid, transcritical and supercritical fluid, and use experiment and numerics for each problem. As it is fashionable to say now, we will build a digital twin of each experimental setup, and this will make it possible for us to gradually advance the experimental diagnostics. We must use Schlieren, I must also add, in multiple planes. We hope we will be able to use thermal imaging with some usefulness, and we also have a setup for bulk temperature measurements, which might also be adapted for this experiment. And then we will use experimental data for code validation. On top of that, we will take one well-known code, OpenFOAM, and we will also model this problem with our in-house open source code, Fiesta, and we will do code-to-code comparison as well. The goal of this process is to produce a validated, physically faithful, reduced order model for transcritical injection, and I will tell you a little bit more about Fiesta. But first, let me start with the experimental part. University of Alabama, Huntsville is not a new player here, and they have a setup with two types of diagnostics, X-ray transmission, which we will not be using, and Schlieren, which we will be using. The setup will be quite straightforward. A prescribed mass flow rate will be produced by running the flow through a choked orifice. It will be straightened out by a honeycomb, and then it will enter a transparent test section with the possibility for Schlieren diagnostics with multiple fields of view. I shouldn't have said multiple planes. That's just my PIV and PLIV background talking. Initial experiments will have injection of CO2 at 30 meters per second into an atmospheric pressure 10 meter per second flow of nitrogen. And it will be captured with a high-speed camera, Phantom 711. And additional diagnostics that we are considering will be a high-speed thermal camera, and also here again I'm saying multiple plane visualization, but it will be more like multiple field of view direction visualization. These are the parts preparing to be assembled. We had hoped we would have some experimental data, but unfortunately the absolutely mission critical transparent component got munched up by the CNC machine, so we will probably get our first experimental data in December, not in the end of October as we had hoped. Now back to numerics. I already mentioned OpenFOAM and Fiesta. OpenFOAM is a known quantity. Fiesta models three-dimensional two-species compressible viscous transport equations in their conservative form. It uses a fifth-order Wien of 5 finite difference scheme for advective terms. It uses a fourth-order central difference scheme for pressure gradient and strain rates. And it uses a second-order Runge-Kutta integrator for time. Important about Fiesta is that it is highly portable, parallelizable, to a certain extent, you could say architecture agnostic, and it can run and optimize itself both on CPUs and on GPUs. And we built a mini supercomputer with an absolutely beastly GPU specifically to run Fiesta for this problem. Our initial computation domain was similar but not identical to the size of the test section in the experiments that will be conducted at Huntsville, and it will be the same materials and the same velocities. We started with a quick two-dimensional run and quickly ran into an issue. If you look here, if you take a really short domain, what happens is something non-physical, namely the flow below what would be our injected jet is going backwards. So all of you have heard about grid artifacts. Here we have a domain artifact. If you model the more realistic extent of the domain as it would be in experiment, however, the problem seems to go away because we no longer get that weird backflow. Just as a sanity check, we decided also to slightly shorten that domain, and with this shortened domain, you also get very consistent results compared with the 465mm domain. So backflow is a domain artifact. So right now we are working on extending this to the three-dimensional configuration and looking at mixing. Future work, we wait for experimental results, Schlieren and thermal imaging, possibly. We produce simulated Schlieren images from our numerical data for quantitative code validation. We will conduct code-to-code comparisons, and again the goal is to develop a reduced order model which may not necessarily resolve all the flow features, but which will be physically faithful based on conservation considerations and experiment. One important announcement that I need to make here is that we are currently hiring people to work on this project, and I want to hire a postdoc who must be a US person or a graduate student for whom there are fewer restrictions on country of origin. However, either a postdoc or a graduate student must have good C++ programming skills and at least some familiarity with CFD. So my email is on the slide, and to conclude my talk, I must acknowledge and make a statement of my appreciation for the funding from the Air Force Office of Scientific Research.